It's a fingering.
Fingering, that's right, that's right. It's pictures that look like this, which we've all seen, but we didn't know what they were. So they predict that this decays to 0 as you change the control parameter, but with the law, with the exponent 0.58. They predict exactly what this thing here, that's why we went to trouble to measure this with a log-log plot. They predict this law. This is not a square root. You can't distinguish by your eye, but here I'm telling you, this is what they predict. And they predict two other things too. They predict the average, the statistics of the gaps in space. Again, this is turbulence, or whatever the excitement is in their system. The typical, you can see that the typical, there's a lot of sizes of this, but it's some probabilistic distribution, and they predict that the qualities of that probabilistic distribution and the gaps in time. Right? So all this you can see, and they make predictions about all these, and we measured them. And of course, I wouldn't be telling you about this if it hadn't worked out. We have the turbulent fraction. We also have the laminar gaps in time that match their exponent, the predicted exponents. And we have the laminar gaps in space, which do and don't. Remember, our system is two-dimensional, and it's not. And I mean, they make predictions in one space dimension and two space dimensions. But our two space dimensions are different. Here, when I say x and z, I really am talking about streamwise and spanwise, contrary to before. And our laminar gaps in the spanwise direction look quite good. They have an exponent of -1.2 instead of -1.17, the theoretical value. But in x, the streamwise gaps are not as good. But we think we have a good reason for that. It's a non-isotropic system. X and Z really are different, and apparently, according to the theory, it's not that it leads to different exponents, but that you may converge to those exponents. All these things are only true asymptotically. It's a probability distribution. To get the probability distribution, you need to sample an infinite amount of time, and you need an infinitely large domain. And we claim that the convergence for the laminar gaps in X is slower than that for the laminar gaps in Z. But this is a technicality. We think we mostly have it. So here's a film of the kind of thing that you should see. This is shear flow, and this is their kind of favorite model called coupled map lattice. And what you're seeing, we'll show them again, or yeah, this one's going slowly. What you're seeing is what happens near criticality here. Again, this is going to bubble and just remain. It's not a steady pattern. But there's the same percentage of black eventually here. Okay, no, actually it would have to be above critical Reynolds number to be for there to be the same amount. Here's the same amount. I'm sorry, I was wrong here. This is the same amount. You can see in time it's going to go to an asymptotic state. Here it's going to disappear in time. That's that black curve that you see. And one of the predictions of directed percolation is the rate at which it disappears in time. Again, statistically, because this is very noisy, you can imagine. And it's according to this blue curve. And you see we do follow this blue curve. So I can play them again, these movies. Oh, it's still playing. Ah, yes. This is a logarithmic scale in time. So, of course, to get another decade is 10 times, to fill out this curve takes a long, this takes 10 times what this takes 10 times what that takes, and so on. So you need not just big domains, but long times. And yeah, I guess maybe let me play it again now that I've made all this, said all this talk here. We'll start again from the beginning. Here, so this is the black on the left is about at the critical Reynolds number. The one at the right is above the critical Reynolds number. So the one at the right is going to saturate at a finite value. The one at the left is going to disappear. Go. And all these structures that you see are those laminar turbulent bands, but at much lower Reynolds number, the kind of the remnant of them that can exist there. And you see the red one is now going to stay at about this level, here, and the black one is going to decay to
So
zero.
what's your plot? Go back 2 slides. Back one more. That one.
Yes.
Okay, so it's a power law, but so is the suggestion there that so is that saying as you make the domain bigger and bigger and bigger,
Yes.
you're always going to get a 2 spot or not? Or does it say,
No, not if you're below.
so there's a 0 fraction
That's,
there?
yes,
Okay.
if you're below here,
Yeah,
you won't
no.
get one.
Okay.
Now, even we are, of course, discontinuous. We can't go any lower than that, right? But the comparison is with, we still think, especially because we've varied the domains, we still think that it's, we're a finite size truncation of something which is continuous. This is what the other people found, excuse me, that would, no, that's not what the other people, that's,
If it's a power law, isn't
Yes.
it going to keep going down and down and down? As the domain gets, or as the Reynolds number gets smaller and smaller?
no, that says Reynolds number, okay.
Oh, hang on.
Okay, so power law, okay, this power law here is in Reynolds number minus Reynolds number critical.
Right.
So there is a finite threshold here below which you're zero.
Okay.
Um,
Okay. All right.
Okay, right. Now, some people, one might think that, of course, what we did, what the other people did, was do, this is true experiment, and this is true simulation of plane Couette flow in a large box, and this is true experiment of plane Couette flow in a large box. How large? Well, that large. Those were large at the time, or they were considered large. They're very large. They're, I don't know, 100 by 200 or something in terms of the half gap. So they're seemingly large. So those size boxes, and this is the curves that they produced, which is to say, you can see this is the amount, this is turbulent fraction. The minimum they got was 0.4, right? And one might think there's two differences between their things and our things. Their thing is plane Couette flow. Our thing is modified Walef flow. And their thing is a smaller domain, and our thing is a bigger domain. So what we did was we used our equations, the modified Walef flow equations, in their size box. And it's discontinuous, just like, and it's not just discontinuous, it's about like them. The minimum that we get is 0.3 here, as they did, and the minimum here we get is about 0.4, as they did. So it is it's not that we're using modified Walef flow as opposed to plane Couette flow. It's because their box is too small to observe this. As I said, even ours are discontinuous. You can see that a little bit at the end. We cannot go any further than this. But you can see that if we had stopped here, 0.4, we would have quite a different picture of what's going on, and we would not have this, we would only have, say, these points here. We would never be able to say, look at our slope here. Okay? So I think that's pretty much all I wanted to say. Yeah, I thought because the first part, yeah, I think that's it. Despite the fact that I thought that I would run over. Oh, no, I do have this other thing to say. Whoops, yeah, I do have, okay. Hold on. Can't go home yet. Almost, but not quite yet. I think this is a very short story. Hopefully, we'll see. Okay, so here we go. This is about regular old Taylor vortex flow, which I am sorry I haven't presented more of in the class. Let me try and make up for that a tiny bit. Hold on. Is this a good one? I'm not sure. Let's I should have a good one someplace. Okay, so this is the flow between differentially rotating concentric cylinders, and they have different, just like plane Couette flow, they have the two cylinders have different velocities, different angular velocities, and it's just like convection, though unlike plane Couette flow, it's going to act above a critical Reynolds number. You will form vortices, which I think we see here. They're not. It's not very clean. I should find a better movie here. Maybe it's the lighting or something. And then if you increase the Reynolds number further, yes, if they start to have waves in the azimuth direction. So you have breaking of symmetry. You have a breaking of symmetry first in the Z direction. First, your first flow was completely independent of Z. It looked the same all the way up and down the column. But it's still axisymmetric, so independent of theta, independent of Z. The first symmetry breaking that happens is a circle pitchfork where it makes rolls that are just like the convection rolls, except what it's spreading around there is angular momentum. But those rolls are straight, just like Boos's straight rolls. They're straight, they're round, but they're independent of theta. They're flat in theta. But then comes a further instability where they become wavy, like that. This is not very good. Not a very good movie. Is there a better movie someplace? Some of them are too long, too much talking. Let's see what happens here. Yeah. Okay. Here's the appearance. That's pretty clean. Appearance of Taylor vortices. They're trying to figure out, they have some imperfections. You remember in the films that we saw yesterday, there's some imperfections that had to iron themselves out at the very end in those films, and so too, it has to figure itself out. But eventually, it's just going to be rolls that are straight. Now he's increasing the Reynolds number, and there's going to be disorder. Is he doing that? Yes. First you see, not very organized. I need to find a better movie. Now each of the rolls is turbulent. Yeah, not very good. Okay. For another time, I'll find you a better movie. So let's go back here then. Here. You all know this picture. You remember the vortex wave interaction, right? We heard about that just 2 hours ago, so I can skip that. Okay, the point is that in plane co-ed flow, although we show these pictures here, this is not a steady state of plane co-ed flow. We show those structures, but you saw they were coming in, they were coming out, they're kind of, they're there, but they're not there. Whereas in Taylor vortices, they are there. You have this column, and they're there, and they stick around as long as you want. This thing is a real, true property, a true steady state of Taylor vortex flow. So the question is, what becomes of this whole thing when you do have Taylor vortex flow here? Not only do you have Taylor vortex flow, but the vortices become wavy, just like those. And this is now the truth. These are stable, steady states that you can observe in the lab. They're not something that you have to do calculations on and do theory. They're all observable. And here are stills of it, better than the movies I found. This is the laminar state, no features here, no features here. Then this is the breaking of Z symmetry, and you have these rolls, and here you don't see it very well, but it's becoming wavy. That's the movie I wanted to show you. Okay, so these are steady states, and in fact, the whole process was kind of modeled after both Phil Hall and Fabien Wallach worked on Taylor vortex flow, and they were inspired by this picture.
TT did his PhD at Melbourne.
Well, there.
They all know that.
Okay. Okay, so I chose the right pictures here. Okay. So here's some other pictures. These are pictures from Coles, that same Coles that I showed you in the previous, when I showed you the turbulent laminar patterns. Here's Taylor vortex flow, and here's a good picture of wavy vortex flow. So for once, movies are not necessarily better than stills. These stills are better than those movies. Okay? And these are states that you can watch, just go happening. You don't have to catch them in some kind of transient way and freeze them and wonder about them. This is what you observe. Coles, this before bifurcation theory and dynamics had really taken over in fluid mechanics. He published this in 1965, showing how complicated Taylor vortex flow is. This is number of vortices. That's what he called cells, and this is number, so the vortices that stack up here, 1, 2, 3, 4, and this is the number of waves. And then there's the Reynolds number must be here, Reynolds number, right? And he published this picture in JFM, and there was a glass or a plexiglass cube made modeling this, which he offered as a prize to anyone who could explain it. I say in those days they were not thinking so much about, they didn't use words like circle pitchfork bifurcation and breaking of Z symmetry and so on. So, and now we, some of us anyway, know that having a great multiplicity of states is possible. This is not merely a multiplicity of states as we saw it just before, because all of these are observable and hence stable. On the other hand, this is as you increase the Reynolds number, so you're not necessarily you're not seeing all of these possibilities for a single Reynolds number. As you increase the Reynolds number, you go around these, and he showed this with the arrows. Is it still at Caltech, this thing?
I've never seen the plexiglass model.
But you heard of it?
No.
This story, I've only heard of this. Okay, then Andrew Liu and Swinney did this survey, a much larger survey than, this is what Coles had done, had just increased the speed of the inner cylinder. This is changing the speed of the outer cylinder as well. So this is co-rotation, where the inner and outer rotate at different speeds, but the same direction, and this is counter-rotation. Note that, unlike plane co-ed flow, where I said all you need to know is the difference in velocities, this is not the case for Taylor co-ed flow because there's rotation, and we know that we know that a translating frame is the same as a not translating frame, but a rotating frame is not the same as a not rotating frame. Hence, it's not merely the difference in velocities that matters, but the values themselves. So you cannot reduce this picture to a single axis as you can in plane co-ed flow. Okay, so but this path though is very well understood. This is all very nice, but this path is the only one we're talking about. We have Taylor vortices. First, we have plane co-ed flow, then we have Taylor vortices. That's a circle pitchfork, as I said, where the circle meaning a phase in Z. Then there's a bifurcation to wavy vortex flow, where there's another phase that appears, which is the theta phase. And by now, hopefully, if the ideas of the class have sunk in, then you understand all these words and you understand this picture, hopefully. But I know that it's still kind of new, and a week ago, what are we today, Thursday? A week ago, or 8 days ago, you would not have heard these words. But now, these are the words that hopefully you have the vocabulary to understand this, which Coles did not. At least I don't think so. So Taylor and co-ed flow and plane co-ed flow are similar. We're showing this. This is it's theta velocity, like the streamwise velocity, and these rolls are like the Taylor vortex rolls. That's the analogy. So we did simulations with pipe flow code of Ashley Willis, and and here we're showing the Taylor vortex flow, and here we're showing here we're showing the eigenvector. Here's the eigenvector that is responsible for the bifurcation from Taylor vortex flow here to wavy vortex flow. And here is a picture all the way around of the wavy vortex flow. So you see the waves. This is the vertical direction. This is the theta. It's been unwrapped. So this is a whole 2 pi's worth. Here there are 15 waves. So as you go around, there are 15 waves like this. And what you're seeing is positive and negative radial velocity in the midplane. Okay, so now comes the part that's it's really not going to be very long. I know we're now equations again instead of pictures. Let us decompose flow into something which is both axially and azimuthally symmetric. This depends only on radius. And then we have a piece, okay, the k is the axial wave number, e to the I kz. The m is the azimuthal wave number, e to the I m theta. Okay, so the initial flow is I'm calling it co-ed flow, the laminar co-ed flow. It just goes round, just like the plane co-ed flow, or just like the conductive solution, right? It just goes round. Forget this for the moment. We have instability to rolls, those things here. As we were discussing before, the rolls transport this angular momentum, or the azimuthal velocity, such that it is, if you have a roll, such that this part here, the fast-moving stuff near the inner cylinder moves out, and the slow-moving stuff near the outer cylinder moves in. So now your theta velocity, which used to be uniform along a line, is not. It's wavy along a line. So that's what's being said here. This k not equal to 0 means wavy along the z direction. And that's the rolls, and the rolls are this. The streaks are the consequential change in the azimuthal velocity profiles here. And now finally, we're going to have the components that have neither k nor m being 0, and that's the waves. It's not only wavy like this, but it's also wavy like this. Okay? This is just a Fourier decomposition. Basically, we have 0, 0, then we have K not 0, M equals 0, and then K and M both not equal to 0. And in Fourier space, we can, this here is 0, 0. The Couette, forget the mean for the moment. This is stuff that varies in Z, but not in theta. And then this is stuff that varies in theta. So, this is the point that I made, in fact, before, in the original slide. Supposing we have this wavy vortex flow eigenfunction. It looks like, before I wrote e to the I alpha x, remember? And we did that calculation, e to the I alpha x times, forget about I mean, basically this is a product, there's a curl, there's, this and that, but still, basically we're going to take a product, e to the I m theta and e to the I m theta plus and minus gives you e to the 2 I m theta, e to the minus 2 I m theta, and e to the I 0, meaning 1. Everybody agree with that? So you're generating some higher wave number stuff, and you're also generating constant stuff. And so that has a projection onto the 0 Fourier wave number stuff. And that is the question. That is the question is, how is this thing here going to, how is it going to reinforce the rolls and the streaks? Because that was the question there in the Plain-Couette case. So we're going to look at how much this projects onto the 0 wave number stuff. So the 0 wave number stuff has, as far as theta is concerned, there's the mean, the roll, the streak. The mean is how much, okay, I told you not to look at it, but you're going to, because you have all this interacting with itself, you're not just going to have the laminar Couette flow. All of this stuff interacting with itself is going to generate some other Z-independent, theta-independent stuff, which is not equal to this. It's just going to make it vary. So now we're going to measure all that. We're going to measure how this feeds this. And that's what we did. That is to say, we're going to look at the overlap between this. Is this going to feed the rolls and the streaks? That's the question. Here, we don't need it to feed the rolls and the streaks because this is Taylor vortex flow and the rolls and the streaks exist anyway. But it's interesting to know how much it feeds it. In plain Couette flow, we really need for it to feed it because these things don't exist. So they're only produced, and only marginally so, by this product. In Taylor vortex flow, they're produced already by instability mechanisms, by bifurcations, the kind of things that we've been discussing over the past weeks. But it's not crucial, but it's interesting to see how much it feeds it in this case when everything can be measured because everything is steady. And the answer is that the wavy vortex flow does feed the rolls. This is a positive contribution. And it drains the streaks. This is a negative contribution. So it takes from the streaks and it gives to the rolls. And that is, I think, am I right? I'm just going back to this spontaneously. Isn't that is the picture here. You are draining, let's see,
Well, the energy has to be fed in from stresses and motion on the top and bottom walls. So it has to be drained out of the streaks.
So it's drained from the, this is the streaks, and it's drained from the streaks, is what this picture is saying, schematic picture. It's drained from the streaks, and it's going to feed the rolls. Or so it says. Now, that's dangerous. Let me go back and see if that's what really, is that what we found?
I think that's what you said.
Yeah, it drains the streaks and feeds the rolls, meaning we actually measured the nonlinear term based on the wavy vortex flow eigenfunction. We projected it onto the rolls and the streaks. Here's the rolls, because they're in the RZ direction, and this is the streaks, because they're in the theta direction. And that's the picture that we found. And then we made a bifurcation diagram where we looked at the energy in the streaks and in the rolls, and we saw that, well, basically the same kind of thing, that the wavy vortex flow drains from the streaks. It takes from the Taylor vortices, drains the streaks. We didn't find so much this other picture of feeds the rolls. That we didn't find. But this we found, that the energy in the streaks of the wavy vortex flow is less than that in the Taylor vortex flow. We didn't.
Well, it has to be.
It has to be, okay, but fine, but Okay, I'm sure there's good reason for that, but you'll explain to me. But what about this non-feeding here? Is that okay?
Don't know.
You don't mind that?
But, I mean, the only place you're doing work in the system is from the walls and the stresses on us, and then that's driving the streaky flow directly. So that's where the energy has to come into the system to do everything else.
Okay, so that has to
happen.
happen. And the fact that this doesn't, you see the fact, here you have the lines and the circles are the same, and here, excuse me, are different, and here they're the same. So the energy in the rolls of both the traveling, of the Taylor, see, because Taylor vortices and wavy vortices are actual steady state or traveling wave flows in Taylor vortex, so we can actually measure how much energy they have as a function of Reynolds number. We can fix the rolls even when they're unstable to the waves by not letting them become non-axisymmetric. We can produce all of these flows numerically, and we can count how much energy they have. And as I said, here we produced the Taylor vortices and we produced the wavy vortices, and we look how much energy they have in the rolls, and that's the same. And I don't know how to, I never got to talk to an expert about it and see whether that was a bad thing or not. That's okay?
Yeah.
You don't mind that?
Well, I don't have any trouble with the left-hand diagram. I'm still struggling to understand the right-hand.
The left hand,
Yeah, well,
this is this term here,
yeah.
with the inner product with, no?
Yeah, that's fine.
Okay, that's fine.
But
Okay, so I think this is the end of this story. Yes, right, this is the end of this story. Right, so I haven't kept you very long, no, only 2 minutes
that's
late.
the reaching out.
There. Okay, so some of you, right, so that's the end of this